Thank you again for joining us. We're going to go ahead and kick this off in about 1 minute. Today's session is Computer Vision 101, Choosing Your First Vision Project. It'll be hosted by Erica Gilbert, our Senior Customer Success Engineer, part of the Customer Success team. We're excited to talk about today's topic because we work with global organizations across the country, and what we come across is, how do we choose our first vision project? How do we determine ROI? What kind of images do we need? So we're happy to present that today. Everyone will receive and record a copy tomorrow. I will drop my email as well as our sales alias if you have any questions, but do expect a follow-up. A little housekeeping. If you have any questions, feel free to drop them in the chat box. The presentation will go for about 20 minutes, and then we'll take live Q&A. We encourage everyone's questions because we like to hear from everybody, and we'll go from there. With that, Erica, take it away.
Awesome. Thank you, Adrian. Of course, we have a pretty packed agenda, just overviewing ultimately what we will overview. So we'll look at the state of CV, really that ROI and timeline, as Adrian indicated, with the actual live demonstration and Q&A. So what's driving adoption of computer vision? So we've all heard about ChatGPT in the news, and we know that the state of adoption of text-based deep learning applications really has reached a critical mass. And then all signs ultimately really point to that same behavior happening in the computer vision market. And that's really driven by the same model advancements that are happening in text have also applied to the vision space. And that includes advancements in compute processing as well, and the overall economic picture. And then what we'll see and expect to see out of that increase is over $28 billion of growth in CAGR. So very exciting. And the important point of that is, if now is the time you're looking at computer vision application, you're joining at just really the right moment. And so why ultimately do we want to look at deep learning? So we want to look at deep learning because there's so much data everywhere that we can analyze with these deep learning algorithms. So obviously the image systems abound. We have cameras, phones, inspection solutions, security systems, drones. It just goes on and on and on. All of those items can be analyzed the same way humans do, which really is a benefit of considering traditional computer vision, which do have very good applications, but sort of fall down when you have to add subjective types of assessments, or you ultimately have to incorporate different logic and rules that expand and change over time, that really becomes impossible to create programmatically. And so that benefit of being able to learn by example and generalize across a set of image-based examples really allows us to continue automation in a new and powerful way, which also makes tasks and processes for humans way more reliable, making their jobs better, easier, faster. So really looking at that to really move this ultimately forward. And I always like to think about deep learning when trying to explain it to people who haven't encountered it before. Obviously, you can see it's sort of the creme de la creme in the AI space, but ultimately it is it's mimicking the neurons in the brain to learn by example. So looking at how a baby learns objects in space and can understand, that this is something I can pick up and grab. It's by seeing those things over time. And then as the child grows into a toddler, then they know that mommy has given me this apple however many times, and now they begin to associate red and the shape as apple. It's the same way that we're teaching deep learning algorithms to understand our subject matter that we want ultimately to understand. What I've seen a lot in my time working in the deep learning industry is that a lot of time companies understand that deep learning is the creme de la creme of the overall AI space, and they want to pursue the most complex, most challenging, most difficult problems. And ultimately that ends up then staying in the innovation lab and never makes it out of that lab door itself. And so what we recommend when you're looking at computer vision projects is really to think about how can you define this having value in the business? And usually the indicators for that are going to be increases in labor efficiency, looking at how you're reducing any product defects or failures, and also producing speed at which you're operating, whether that be on a production line or in other applications. Because once the enterprise sees the value, they're going to want to take that and hit the repeat button. So definitely look at ROI as you're assembling your overall project early on. And then also look at that timeline. Make sure you have resources available. Make sure you already have a system set up that can identify and acquire the images. And make sure you have at least thought about ultimately how you would deploy this. Are you going to leverage an API to programmatically ping landing lens to analyze your images? Or are you going to deploy that ultimately on an edge device and run that offline? So thinking about those things in advance will ensure that once you get your model and develop that rapidly with the landing lens platform, you're able to take it and move forward to production. And then we want to look at ultimately, is this a feasible project? So not only does it have ROI and a timeline that is going to show a quick win and rate of success, is it possible? So when you look at your images, do you and other people who are subject matter experts in that content actually agree on what those items are? Can you see it? So a lot of times I have seen images that come in for sort of feasibility review, and it's maybe 2 pixels out of a 2,000 pixel image. How are we going to be able to teach an AI to find that if you can't even really see it visually? Also, there may be environments where it's not possible to consistently capture that image, and you need to think about how that's going to happen, because that's ultimately what you have to show the AI to both teach and predict and analyze overall. So these are just some of the examples that you would want to think about in organizing your overall application in advance about what ultimately you're teaching the AI to understand, that ultimate input into the model. But also you want to think about what is the output. So based on what I'm showing the model and what I've seen when I train the model, does it meet the accuracy levels I need for it to match or meet an ROI? So for example, if we think about ultimately, there's a piece of data in the market that states the average human is about 80% accurate. And you have an AI system that's 70% accurate. Maybe you wouldn't want to consider replacement then using the AI. Maybe you would want to augment that with for the human to actually do that review with the AI as an assist, sort of like a robotic arm. But looking at all of those components of ultimately how that output is received from your model, and looking at what you do then next. So are you taking that information about, in this case, we're going to look at metal casting as a use case today, and we're going to look at 3 different flavors of how you can analyze and identify information in those metal casts. Do you want to take that information and then ultimately understand where the defects are, or does that not matter? And where does that information go in the business itself? Is it passed down to different types of teams who are working with the metal cast themselves? And these are some of the hallmarks of overall best practice when you move from the point of understanding that yes, your project is overall feasible, and we want to look at what actually you can do to gather that data. Always, there'll be a point and a trade-off where showing more data to the model is not going to improve performance, but you end up reaching pretty high levels of amounts of data once it gets that trail off. So the more image examples, the better. And the more the model will be able to understand exactly what it is when you say, hole or scratch versus a good metal cast. And then obviously that translates to being the more simple or consistent the use case, the less data ultimately you need. If there's a lot of variation in how hole or scratch might appear, you're going to need many more examples. The benefit of the platform is that you can start with as little as 10 of each type of class or label you want the model to understand. And you can iterate that on over time. You can continue to add data until you get to a state of performance you feel is good for production, or you can even put that model, out in the wild, so to speak, and gather additional data and then feed that back to the model to improve performance over time. And you'll see that as part of the demonstration today. It's also really critical to ensure you collect as similar number of examples of each type of label as possible. We really want to look, in this case, you see we have pretty small data set here of just 6 examples of hole and scratch, but they are even here. And that helps the model not bias towards one type of item you want it to understand. So if you have 25 examples of hole versus 2 examples of scratch, the model is going to understand and be looking for hole in a more robust manner. And then also we want to ensure that those examples that you're including in your data set represent what real life looks like. So in the example of our metal cast use case, there might be different lighting that ultimately happens where these casts are analyzed day in, day out. So you want to make sure that you're able to either restrict the environment so the light doesn't impact the view of the image capture, or capture the data in different lighting variations. So that way the model understands that the variation of good could actually look quite different depending on the time of day. And this is just an example to show here when we look at that best practice for data gathering, is that we want consistency. If it's a classification, really you're typing the image of a whole scene in one way. So we want to look at lighting, as I mentioned, orientation, the camera position, all of those things to create consistency in how we're capturing that data. The model itself will support a variety of different type of images. So thinking about that, maybe how you're going to be applying information to those images downstream. Will they always come in originally and then transform to different image types? Again, you want good coverage of your object of interest. Here we see, actually, now you can see the bottom part of the slide here. This is a good example for this metal casting use case on the left, and on the right here, it's really not a very good example. It's probably also not something you would see in real life, but it showcases that the model is trying to learn what good looks like. And in this image, it has pretty clear understanding of focal point of the metal cast itself. There's a lot less other noise in the image. On the right here, there's a lot of different things going on. And so it would take more data for the model to actually be able to decipher and understand. And ultimately, I might get confused very often on what it's ultimately predicting. But now we're going to step into seeing this all in real life. Ultimately, now that you've found something that has ROI, that you have data, and you can have resources available to come into Landing Lens and build these models super rapidly. So we'll see how we can organize and upload our data with a classification model. We'll review and understand that overall model performance. And then we'll look at, okay, now we've understood with these metal casts what is good and what is not good, but maybe we want to understand where actually a scratch or hole and what those defect types are. And we really have 2 different options for that. We can look at putting a bounding box around those defects, or we can use a segmentation model to create that pixel level precision so that maybe an automated system can fill in those defects straight away without additional or much overhead from a human. So your key takeaway really is this platform will allow you to reduce your time to value and create end-to-end computer vision applications simply without a data scientist. Though, if you are a data scientist, I'm sure you'll enjoy all of the metrics and stuff that you'll see in the platform today. So what I'm going to do now is actually, you see I'm on the homepage of the platform, and I'm going to start by actually creating my project. And because I have my data organized, it's very straightforward for me to come in and just drag these in. I can actually review and see the different images. It looks like my second folder, which is great to be able to have that quick sort of preview. And now I see that my defects of no good are available. This all looks pretty accurate, not quite balanced here, but pretty close. And so I'll just press the upload button. While I'm doing that, I can go ahead and sort of name my project. In this case, though, we have these nice icons that indicate what type of project this is. I like to also include it in the name and then who ultimately created the project itself. And now I see all of my images are uploaded and they all have the data as a ground truth or the actual, label itself available to be used to teach and show the model what ultimately good versus not good is. And we've really simplified that process. So all you have to do is hit that train button, and we're going to leverage our state-of-the-art deep learning models that have been optimized over time to learn what ultimately that is. So I'm going to hit the fast forward button here or pull the casserole out of the oven. The training happens pretty rapidly, but I want to make use of the time we have here. And I can see that this model is actually performing really well. So we have high performance score here that really help us understand the model performance. So we withhold a percentage of the data that you've provided as labeled and give that to the model as a quiz, really to say, did you get this right or wrong? And then based on that, we can come up with these precision and recall metrics. In this case, it's very highly performant. We see out of the roughly 7,000, 8,000 images, it's only missed 36 of them. So I can actually review them and make a decision about, should I add more data? Should I look at other methods of identifying what the defects are to further fine tune this model's performance? Where is it seeing and learning what it thinks is making this image no defect or good defect? And we see, there's maybe a little bit of confusion here. It's picking up on stuff that maybe actually I need to go have a chat with my subject matter expert and say, is this actually a defect or not, or is this actually good? So I can further fine tune that. But what I also know about this entire dashboard is the confidence scores of the model here. So how confident is the model from a 0 to 1 value in saying that this is good and it's no defect? And the majority of these are below 50%. So I can actually use that as information in my downstream process to say, if the model makes a prediction that's below 50% in confidence, I'm actually going to have a human come out and review ultimately those metal casts. So a lot of information that you get just from this dashboard alone on really understanding the overall model's performance. But let's say ultimately we know what good and not good looks like. We've seen how some of this in case is predicting good with no defects. And we think that we could improve the model's performance by actually using detection, so localizing with bounding boxes where those defects are. So I would go through the same process again, ultimately loading that data, labeling a minimum of 10 examples of where those defects are in a very intuitive, easy to use interface here. So here we see hole. And if there was actually a scratch, I would just switch here or crack and create that within this set itself. And once again, once I have enough data, come in and hit that train button. And here we can see, we have way less data in this overall project. I get a nice snapshot here of that as well. But I can also come in and deploy, and I'll show you that in just a second with the segmentation model here as well. A lot of other things happening here where the model actually, once it's been trained for the initial time, when you load new data, it's going to come in and try to recommend what it thinks might be scratches or holes. And you can see that little dotted line there indicating a likely scratch or hole. So it helps accelerate that time to actually create your first initial model. We're tracking new models, even outside of classification, which is very rapid, with detection and segmentation in hours rather than weeks and months. So then ultimately we look at, okay, what's the next level of precision and understanding and showing a model what these defects are. And that's going to be segmentation. So you're really segmenting out with pixel level precision what ultimately is a scratch or hole. And you can see I have very easy tools where I can come in and draw that information. I mean, let's say that this actually was a scratch. It becomes very straightforward to include that, show examples of what those are, and it's down to the pixel level on the actual image itself. So it really refines and removes all noise of ultimately what something is when you're doing that example-based learning. So here we've actually trained this model with a relatively small amount of data, but I want to bring this model to the manufacturing floor and show it some new examples, gather new data, and then actually test it as well. So what I can do is just hit the predict button here, and we'll use actually just an image of myself. Boop. And it's going to run a prediction and inference request to this segmentation model. And the expectation by using my webcam here is that it's not going to be able to predict anything because it hasn't seen anything like that before. And that's correct. So we can actually see the prediction here as no labels, but you can imagine if you had this set up on the manufacturing floor, you could rapidly gather new data, add it to the model, retrain, and improve performance. And there are a lot of options ultimately for that deployment. So you can leverage a cloud-based deployment, which is easy to version and create within the platform. So right within the deploy page here. And you can see we have the Python information, JavaScript, and a curl command to leverage that inference request to this particular segmentation model. And you can also even just scan your mobile phone and upload images that we will actually store to make available to add back to the project itself. In the build mode, it'll show as unlabeled. You can come in and label it and then retrain your model. So you'll get still versions of your model when you hit that retrain button. So if you add new data and it makes the performance lower, then you can always go back to that earlier version of the model. But that's the content I prepared to walk you through how you choose your custom vision or computer vision project, and then ultimately perform that end-to-end in the Landing Lens platform with simplicity and ease. And so I think now we'll turn it over for questions from the group.
And we actually have a great question here, Erica. My question is, how do the credits work on Landing AI labeling platform? How credits are sized per point, image, or label? Does that make sense?
Yes. So I know we have different pricing packs, and that changes how the credits work. So probably what would be best is to spend a little time with our team and get an understanding of what you're looking to try to do, and ultimately then what the size of that is. And then we can give you really detailed information about how that credit works for each of those points.
Great answer. And again, we will be following up with the recording and to book time with our field. So look for those today. I'll make sure I get things actually a little earlier. Do we have any additional questions? And if so, feel free to raise your hand. I can unmute you. Here's a new question. Platform stores model deployment. Does that make sense, Erica?
Yeah, perhaps if you could expand, but I'll take a pass at what I think you're driving at. So we do store for the cloud-based deployments the model that you're leveraging and keep that as a version. We do the same when you create an edge-based model. And so there are options with our landing edge application where you can either download the model and then store it in landing edge and pull the model up, or it can be accessed online. But we do maintain versions. I believe it's in perpetuity, but I can double check on the exact timing of that. Does that help answer, or is that what you were driving at?
And for the user who asked that question, I actually unmuted you. So if you want to go live and re-ask that question, we're here to help. Okay, looks like
Yeah.
that's good. And then we had another question around, do we have to pay for model deployed on Edge? Or is there a pricing model for Edge?
Yes, there is a separate pricing structure for edge deployments. And so we usually think about that as in licensing the actual application rather than number of models. But that's something we'd be happy again to just spend a little time understanding what you're trying to do. Make sure your PLC PC meets requirements to load and process models. But yes, the landing edge deployed downloaded models has a different pricing structure, which can be used in combination with cloud as well. So we have customers doing a wide variety of things, which is great because it gives you true flexibility to work in different ways and set up applications, right at the edge or online.
Excellent. Thank you, Erica. And let's see, we have time for a few more questions. I've actually dropped my email as well as our sales alias. So if you'd like to reach out to our field team today, we will make sure we do a follow-up. And just as a call to action, feel free to join our community. It's a very interactive community where we have product, engineering, marketing, sales, all responding to questions, as well as our partners. In addition, we encourage everybody to obviously sign up for a free 30-day trial of Landing Lens so that you can get started on your first computer vision project. And this is a weekly session. We'll be publishing our calendar. We are now kicked off our Q2, which will run through the end of October. And it'll be a mixture of live topics in addition to office hours. So those who do sign up for Landing Lens, we will do an office hours where we'll take questions specifically around use case, new features, things like that. These are reserved for more topics where we actually kind of give you a little bit of our thought leadership. Okay, if there are no more questions, we'll go ahead and wrap this up. Thank you, Erica, for a great presentation. And thank you, everybody, for giving us your time this morning. I hope you found choosing your first computer vision project useful and helpful. And again, you'll see a follow-up with the YouTube video, and we welcome the opportunity to learn more about your use case or what we can do to help. Have a great day. Thank you.
Thanks, everyone.